Welcome to This Explainer. Today, we're diving straight into the fundamental architecture of Linux to demystify the critical boundaries that keep our systems stable, secure, and, well, actually running. If you've ever wondered what's truly happening under the hood of your servers or containers, you are exactly in the right place. Let's get into it. Real quick, here's our roadmap for today. We're going to start with the two worlds of Linux, see why apps need chaperones, look at how we cross the kernel boundary, trace the actual journey of data, and finally, unpack what all of this means for Docker, Kubernetes, and eBPF.
Right, so to kick things off, we have to ask a fundamental question about how computers actually work. Why isn't your web browser, or say, a random Python script, allowed to just send instructions directly to the CPU? Like, why can't they just do whatever they want, whenever they want?
Well, imagine if they actually could. If every single application had direct access to the hardware, we'd be looking at an absolute disaster scenario. Think about it. A simple, everyday bug in a web server, like Nginx, could accidentally overwrite your entire SSD. It could delete the operating system, overwrite other users' private data, or corrupt core memory. Basically, you'd get total, instant system collapse. Your state-of-the-art server would literally turn into a very expensive space heater.
Which brings us to Section 1, the two worlds of Linux and this fundamental architectural split. To actively prevent that total disaster, the operating system intentionally splits the entire computer into two strictly isolated worlds, user space and kernel space. User space is where your everyday applications live and work. We're talking Chrome, Python, Java, your MySQL client, all of that. Kernel space, on the other hand, is the protected, highly privileged realm. That's the VIP section where the core system managers live. Stuff like the process scheduler, the memory manager, the virtual file system, and the device drivers.
Moving on to Section 2, let's talk about why apps need chaperones and understand these application limitations. So let's look a little closer at what those user space applications can and actually cannot do on their own. While your apps can happily execute their own code and use the memory they've been specifically assigned, they have some massive hard restrictions. They are strictly forbidden from directly controlling the CPU, accessing the hard drive, touching the network card, or modifying memory page tables. Believe it or not, they can't even spontaneously create new processes from scratch. And because of these extremely tight restrictions, applications are completely dependent on kernel space. You can think of the kernel as the ultimate general manager of the entire computer. It holds the exclusive, absolute rights to touch the physical hardware. So anytime an application wants to do something meaningful outside of its own little bubble, it has to politically ask the general manager to do it on its behalf. Section 3, crossing the kernel boundary. How do these two completely separate worlds actually communicate? So how does a user space app actually get the kernel's attention when it needs to, read a file or send a network message? The answer is a system call. A system call acts as a highly secure border crossing. It's a heavily regulated, programmatic interface where standard commands like read, write, or open are formally handed over to that general manager we just talked about. Now, what's really fascinating here is that this boundary isn't just a software concept. It is physically enforced by the CPU itself at the hardware level. The CPU literally switches between different execution privileges. When it's running in user mode, the CPU enforces strict limits, totally blocking any privileged instructions. But the moment it enters kernel mode, the CPU unlocks its full capabilities. It can control the hardware, memory management units, and disable interrupts. It essentially gets the keys to the castle. To move between these two modes, the system performs what is known as a context switch. Every single time an application makes a system call, the CPU literally has to hit pause. It saves its current state, elevates its privileges to kernel mode, completes the requested task, and then switches all the way back. As you can probably guess, it's incredibly secure, but it is a highly computationally expensive process. All right, Section 4, the journey of data. Let's trace these application requests in action. Let's trace a real-world journey here. When an app wants to read a file, it never just touches the SSD. No way. It calls read, which a standard library like glibc wraps up nicely. Boom, a system call triggers a context switch. We drop down into kernel space, navigate the virtual file system maze, hit the ext4 and block layers, until finally the NVMe driver physically grabs the data from the SSD. Only then is the data safely passed all the way back up to the application. It's the exact same story for a network request. The process is heavily layered. The application just calls send. It is totally blind to Ethernet protocols or IP layers. It just tosses its data over the boundary into a socket buffer.
The kernel then takes over all the heavy lifting, processing that data through the TCP stack, dropping it down to the IP layer, and finally handing it off to the network interface card's driver to be physically transmitted.
So why go through all this trouble? Well, this seemingly tedious separation is exactly what gives Linux its legendary stability and security. Because applications are walled off, they're isolated in their own separate memory spaces. App A absolutely cannot snoop on or overwrite App B's memory, and neither of them can touch the kernel's memory. If a program crashes in user space, it's completely contained. It's not going to bring down the kernel or the whole system with it. Section 5. Docker, Kubernetes, and eBPF. Let's talk about the modern cloud-native implications of all this. Let's pull the camera back for a second and see why all of this foundational theory is absolutely critical for modern cloud engineering. And the most crucial point here is addressing a massive, extremely common misconception. Unlike virtual machines, Docker containers absolutely do not pack their own kernels. Let me say that again. All containers share the exact same underlying Linux kernel as the host machine. When you really look at it, Docker is essentially an incredible illusion built entirely in user space. Containers are just regular user space processes wrapped in some very clever isolation features. What this means in practice is that if you're running a massive Kubernetes cluster, you are fundamentally relying on that one single kernel, that one general manager to safely handle every single system call, network request, and memory allocation for every single container on that node. This shared architecture is also exactly why eBPF is such a revolutionary technology right now. By allowing custom, highly secure observation programs to be loaded and run directly inside kernel space, we get to bypass user space completely. eBPF triggers immediately upon system calls or network events. It can observe process and file system activity at lightning speed precisely because it operates without that massive performance cost of context switching back and forth to user space. It's a total game changer. When we look at this complete vertical architecture, we can clearly see the solid line dividing the high-level application logic up in user space from the heavy privilege lifting performed by the kernel down below. It's honestly a beautiful, elegant system of checks and balances that keeps everything running. Which leaves us with a fascinating, kinda provocative thought to take away. If container isolation is really just a user space illusion resting entirely on a single shared kernel, understanding how to monitor and secure that kernel might just be the absolute most important job in cloud computing today. Think about that the next time you spin up a container. Thanks for joining me on this explainer and keep learning.